All right, let's talk about unit vectors. A unit vector, we tend to, instead of putting the little vector symbol on top for a unit vector, we give this a special symbol. We put a hat on there. We would say U hat. What makes this a unit vector is it has magnitude 1. So I claim that this vector, U hat, is 3/5, comma 4/5, is a unit vector. Let's check and see. His magnitude would be square root of the x squared plus y squared. So I want 3/5 squared plus 4/5 squared, just Pythagorean. To square a fraction, just square top and bottom. That's 9/5 plus 16/5, or 20/5, squared top and bottom. That's square root of 25 over 25. That is, square root of 1 is 1. That guy does have length 1. Okay, what if we got a vector that's not a unit vector, but we want to turn it into one? So let's say we want to find a unit vector in the direction of, let's call him W equals 5, 12. So I want a vector that points in the same direction as that one, but has magnitude 1. Well, then we just rescale this guy. We divide him by his own magnitude. Our unit vector we are looking for will be take that guy and divide him by his own magnitude. So let's find its magnitude. That will be square root of 25 plus 144. Square root of 169, that's 13. So I'm just going to take this guy and divide him, or take 1/13 of him, and then I can just distribute in. That's how we do scalar multiplication. So now that guy points parallel to W, points in the same direction, but only has a length of 1. Okay, now we got a couple of special unit vectors called the standard basis vectors. These are I hat is 0, 1. Sorry, 1, 0. And J hat is 0, 1. These are unit vectors, but they're special. I hat points toward the point in standard position, 0, 1. J hat points toward the point 1, or set that backwards. I hat points toward the point 1, 0. J hat points toward the point 0, 1. I hat points along the x direction, J along the y. If we went up one more dimension, it would be I, J, K would point straight up the z-axis. Okay, now what's interesting is every vector in 2 dimensions can be expressed as a linear combination of standard basis vectors. That sounds complicated, but this is actually the easiest thing we do all semester. So let's say I want to express V, let's call him, I don't know, 7, 9, as a linear combination of standard basis vectors. Okay, so I'm going to prove to you how we do it, and then the actual doing it is incredibly easy. First, V could be written, if I wanted to, as 7, 0 plus 0, 9. Remember, to add vectors, you just add the x's and add the y's. Look, that would be 7, 9. Now, I could, if I wanted to, write this guy as 7 times 1, 0. Pull out that scalar 7 and play the same game here. Write this guy as 9 times 0, 1. But look, that right there, that's what I called I. And that right there, that's what I called J. So I could write V as 7I plus 9J. Now, we're never going to go through all that work again. I just wanted you to believe that it was true. The point is, this is one way to express a vector. Another way to write vectors is using these i's and j's, and we tend to do this a lot in physics. So we just want to be able to go back and forth. These two things mean the same thing. Notice here we have the brackets, here we don't. So if I wanted to do the same thing with W is negative 400, comma 17. Then I would just write W is negative 400I plus 17J. That's it. There's no work to do. You literally just write it down. Put that number in front of I, that number in front of J, and put a plus in between.